However, if after some multiplication will be equal, one of the value here, let's say, here is negative 140. These two remain positive. Only the first value is negative 140. If any value is negative, it means that the current solution, the feasibility is no longer feasible. Then we have to use the dual simplex to recover the feasibility. So this is the first case of sensitivity analysis, changes of right hand side. So today, we're going to look into details for the second case. The second case here is, we want to find the range. We call it as a feasibility range. Okay? Later on, we will also have the optimality range. We only invoke the optimality range if we want to find the range for the objective function. If we want to find the range for the right hand side, we call it as a feasibility range. We use the keyword feasibility. So as you can see for this example, 4.10. By referring to example 4.8, it means that you have to scroll up to the original case study from example 4.8. Suppose we are interested in determining the feasibility range for the operation 1. So this is your operation 1. This is your operation 1. Then this is your operation 2. Then this is your operation 3. Suppose we want to find the range for operation 1. It means that we want to inspect what is the minimum value and also maximum value for the right hand side of operation 1. See, for example, we want to know about the changes. What is the minimum value and also maximum value for this operation 1? Once we get to know the minimum value and also maximum value, so that we can make the adjustment by ourselves in order to ensure the feasibility. If we're going to make a changes that outside of this range, it means the current solution will no longer be feasible. So that's why we want to find the range. It will be easier for the decision maker when they want to make a decision, or when they want to make an amendment or adjustment. So right now, if you want to know the feasibility range for this operation 1, then you just have to cross a triangle. Cross a triangle only for the operation 1. 430. This is 430. If you want to find a range for this operation 1, you just write like this. Cross the triangle. This triangle we call it as a changes. 430 cross a triangle. This triangle is unknown. Later on, we want to find it. What is the minimum value and also the maximum value? So that's why you will see something like this. B inverse multiplied with 430 cross a triangle. 460 will still remain the same because we are not interested to find a range for the second operation, and also we are not interested to find a range for the third operation. So after some simple multiplication, you will get something like this. 100 plus changes over 2 for x2. 230 for x3. Then your x6 here is equal to 20 minus 2 triangle. Then after that, we're going to let all these to be greater than 0. We're going to let all these to be greater than 0. Then, what is the next step? Our next step here is that we want to find what is the intersection area for this triangle. For example, we focus on the first one first. First one is 100 plus triangle over 2 greater than or equal to 0. Then we want to find the range, or we want to find the value for this triangle. So triangle over 2 greater than or equals to
negative 100.
Negative 100. Then this one will equal to negative 200. Okay? This is the first one. For second one, we have 230 greater than or equal to 0. That one, we didn't involve any triangle. So that one we call it as independent of a triangle. Okay? Then how about third one? The third one is 20 minus 2 triangle, then greater than equals to 0. Then negative 2 triangle greater than equals to negative 20. So 2 triangle less than equals to 20. Then triangle will be 10. So right now we want to use a number line to find the intersection area. For the first one, we have negative 200 and then we have 10. The positive will fall on this side. Then here will be negative 200. Okay? Greater than equals to negative 200. So you will go up this side, move towards the right hand side. Greater than equal. For this one, less than equals to 10. Less than equals to 10. So move toward the left hand side. Then after that, you will find the intersection area. This is the one. So it means that your changes must be made between 10 and also negative 200. That's the meaning here. See, the changes must be made between 10 and also negative 200. What is the original value for operation 1? 430. 430. If you want to talk about the operation 1 capacity, then we have to pass in this value. Originally it's 430. If 430, then plus this one is equals to 440. Then how about this one? 430 minus 200 is equals to 230. So it means that your right hand side, you can make the adjustment between 230 and also 440 in order to remain the feasibility of the current solution. Okay, get it? So this is the way of doing. As you can see from here, this is 440 and then this is 230. Then right now, if you go through the question, this is the one. Suppose that the capacity of operation 1 is changed from the current level of 430 to 400. 430 to 400, we want to find the changes. The changes here is 400 minus 430 is equals to negative 30. Is this negative 30 fall inside the range? See? This triangle stands for the changes. The changes here is negative 30. Is that fall inside the range that we found out previously? Negative 30. Is that fall between this range? Negative 30. That's right. We can go up to negative 200. So negative 30 still fall inside the range here. It means that these changes were going to give you the solution that will still remain the feasibility of the current solution. So what is the current solution? I highlight again. Your current solution here is equal to the original optimal value from example 4.8. This is the current solution. Okay? So right now we come back to this case. 100 plus changes over 2. So how to get this part? This part here is, you have to store up to this one. This is the one. 100 plus changes over 2. Right now the changes is negative 30 from 430 to 400. So 100 plus changes over 2, you're going to substitute in. The changes value here is negative 30. Then after some simple calculation, your x2 right now is 85. Your x3 is 230 and then your x6 value is 80. Okay, so this answer will ensure that the current solution will still remain feasible. That's the meaning here. If from the very beginning, let's say after some calculation, this value is equals to example. After some negative 300. If it's equal to negative 300, definitely it's out of the range. So if out of the range, even though you substitute inside, all these values will no longer be visible. That's the meaning here.
ITOR.
So we move on to the third case, that is the addition of new constraint, where you're going to add in the new constraint. Initially, we only have 3 constraints that involve the operation 1, operation 2, and also operation 3. Right now, we want to add in one more operation. As you can go through this case study, example 4.11. Suppose that toy is changing the design of its toy, and then the change will require an addition of 4 operations. See, this one 4 operation. If you scroll up to the example 4.8, we only involve 3 operations. Right now, we're going to add in one more operation. Then what is the information for the 4 operation here? The daily capacity of the new operation is 500 minutes. Daily capacity for the operation, for this 4 operation is 500. So your right hand side is 500. Times per unit for the 3 products on this new operation are suggested in 2 options. We have 311 and also 331. So 311 for the different types, for the 3 products. So 311. If you want to know what is your x1, x2, and x3, you can scroll up to the definition in example 4.8. So this is the first suggestion. 3x1 plus x2 plus x3 less than equal to 500. Let's say we want to add in this new constraint. Then we are going to see what happens. This constraint is redundant. Redundant meaning here is something that is extra. You are not going to use it at all. Because it is satisfied by the current optimal solution. So our current optimal solution is x1 equals to 0, x2 equals to 100, and also x3 equals to 230. How are we going to know about this value? How are we going to know about x1 equals to 0, x2 equals to 100, and also x3 equals to 230? Where can we get this information?
特征用纸在上面。
Scroll up to example 4.8. See your x1 equals to 0, x2 equals to 100, x3 equals to 230. You can get it from an optimal table. This is your optimal table by using simplex method. Your x1 equals to 0, your x2 here is equal to 100, then your x3 here is equal to 230. We get it from here. Okay? This constraint is redundant because it is satisfied by the current optimal solution. Why do you say that? You can try it out by substituting the x1 inside here, x2 inside here, and also x3 inside here. See whether your left hand side is less than or equal to 500 or not. Okay, you can give it a try by substituting x1, x2, x3 into here. Then you will get the answer of 3 multiplied with 0 plus 100 plus 230. So the total summation for your left hand side is equal to 230 plus 100, 330. 330 is less than equal to 500. So that's why we say that this constraint is redundant because it is satisfied by the current optimal solution. So that's why there is no simplex calculation is needed. How about for the second option here? How about for the second option? If you're going to have a new constraint of 3x1 plus 3x2 plus x3 less than or equals to 500. equation here. So same thing, we're going to plug in the optimal value for x1, x2, and x3. We want to check that whether our left-hand side is less than or equal to 500 or not. For this case, after we substitute in, we can see that what's the value? The left-hand side value is 530. 530 is greater than 500, so it's not satisfied this constraint. If not satisfied, then we have to involve the simplest calculation here. For example, all this information you have to copy from the optimal table of example 4.8. The one that highlighted in front of you, you can get it from the optimal table. This is the one. Just copy, and then paste it later. Okay? Just copy, and then paste it here. This is the one. Okay? Then this new constraint that we want to add in right now, you just put into here 3x1 plus 3x2 plus 1x3. Then less than equals to 500. This is the one. Less than equals to 500. If you want to change to standard form, of course we have to add in a Z variable. If you scroll up to the optimal table of example 4.8, I think it's only involved up to access column. Right now, because due to the new added constraint, we have to add in the Z variable to make it standardized. So that's why we have to add in one more column, x7. So it's 1 that equals to 500. Once you add in this new constraint, then you will see that it's going to cause first two row we don't have a basic variable. See? First two row, why we don't have a basic variable? Supposedly this one will be your identity column. But because due to the value of 3, the 3 is come from the new constraint. Due to a value of 3, so this one is no longer the identity column. That's why you put the dash here. Supposedly this is your identity column. But because of this value 1 come from the new constraint. So that's why this one is no longer the identity column. We don't have a basic variable. Because we don't have a basic variable, we cannot solve it directly. Okay? We have to update it first. So how are we going to update it? The way of updating is similar to the concept of big N method. How are we going to update it here? Come, give it a try. Let's say right now, here, for the big N method, we copy everything. Except the Z row, we cannot copy because we want to find a new value for the Z row, for the big N method. But for this, we copy the Z row as well. Except this one, we cannot copy. Because right now our purpose is we want to make this one equal to 0 and also this one equal to 0. See? So, how are we going to update this table? We're going to take this value of 1, the 1 we have to multiply with -3. Can you guys see or get confused about it? You guys know what am I talking here? Yes or no? Our purpose here is that we want to make this equal to 0 and also this equal to 0. So that these two columns can be the identity column. So that's why when you update for this iteration, we only copy these 3 rows and also the Z row. For this, we cannot copy because we want to update it. But for the big N method, we copy everything except the Z row. Because we want to update the Z row. Because we want to remove the value of 100. Okay? So we copy the first 3 rows, paste into here. Copy the Z row, paste into here. Except X7 row you cannot copy. We have to refigure out again. So the calculation will be the 1 we have to multiply with -3, then cross this one 3, then will equal to 0. Then the 1 here we have to multiply with -1, then cross this one, then we will get the value of 0. Okay? So the calculation will be 3 over 2, x4. So we are looking for the x4 column. Then here is 3 over 2. We're going to put inside here. 3 over 2. But will become negative is due to a negative z. If you are using the positive z, then you just put the exact value 3 over 2 without negative sign. The next non-basic variable is x5. Dual constant for x5 is y2 minus 0. Plug inside the value for y2, you will get 5 over 4 for x5. So we are looking for the x5. Then will become 5 over 4 here. Because we are using a negative z, so 5 over 4 will become negative 5 over 4. Okay? So right now we have filled up the z value for the non-basic variable. x1, x4, and also x5. Then how about the basic variable? We have the basic variable 2, 3, and also 6 here. How are we going to figure out the z value for 2, 3, 6? As you can see from here, the z value for 2, 3, 6 are all equal to 0. Why? Ryan? Can we use the same method? Because we find the z value for the non-basic variable, we also look for the dual constant, right? So if you want to look for the dual constant for x2, so go up to the dual model, find the dual constant for x2, then substitute in y1, y2, y3. You will see what's the value here. Give it a try. Give it a try for x2 dual constraint.